Hello PLP Geometry, and welcome to the sixth and final video from Unit 3. We are almost done talking about these random topics with triangles. And actually, this is going to go beyond triangles and talk about like more polygons, but we're going to talk about an idea called symmetry. Okay, I wanted to stick this in this unit because we did talk about isosceles and equilateral triangles, so I do want to talk about the symmetry behind those shapes. So again, this is Unit 3. More with triangles, and again, this is the sixth and final video on symmetry. Now, there are two types of symmetries that we're going to talk about here. Okay, so the first one is called reflectional symmetry. Reflectional symmetry. So again, if you do remember the early parts of Unit 2 where we talked about reflections, this is very, very close to that idea, right? So again, what we're doing here is we're taking a look to see if we have a reflection. Do we have a reflection that maps a figure onto itself? So when we were doing reflections back in Unit 2, we had two separate triangles, right? Like a pre-image and image. Now we have just one, and we want to see if we can draw a line through our figure so that if we reflected on that line, it would reflect onto itself, almost like we're folding it in half, right? So I want to start with the equilateral triangle first. We're going to do both the equilateral and isosceles. I want to start with the equilateral triangle first because it's a little bit nicer, right? So let me just draw this equilateral triangle. So an equilateral triangle, you can hopefully remember from earlier in this chapter, right, that an equilateral triangle has all three sides congruent and all three angles congruent. So do my best job to do that. I'm going to mark all three sides congruent, all three angles. Now, as we get into bigger polygons, right, 4-sided, 5-sided, 6-sided, when a polygon has three congruent sides and three congruent angles, we call it a regular polygon. So in parentheses here, we're going to talk about the word regular. So when you hear something called regular, that means it has all congruent sides and all congruent angles. So we're going to say all sides and all angles congruent. And again, I'm trying to leave some space because I'm going to do the isosceles triangle over here to the right. So if we take a look at this equilateral triangle, can you kind of turn it in your head? Or, and I don't want to say turn, I shouldn't say turn. Can you fold it onto itself so that, you know, you'd create like a crease through it? Hopefully you can see that this one right here, this line, going straight down through that top angle, right? That's going to fold this guy in half. If I were to take the triangle and flip it around that line, it would just become itself again, right? So that's one line of, we call it a line of symmetry. Now, there's also going to be a line going this way. And again, it might be tough to see. You got to kind of turn your head. But now if we fold it along that line, that would also be a line of symmetry. And there's also one going this way. And again, if we folded it onto itself or flipped it along that line, it would map onto itself. So an equilateral triangle is actually going to have three lines of symmetry. Now, let's talk about an isosceles triangle. Okay. Okay, so for an isosceles triangle, let's draw like a kind of a wide and short one. So remember, isosceles triangle has two sides congruent. So I drew it kind of wide and short so that these two sides, remember they're called the legs, they're going to be the congruent ones, and that would mean that these two angles are congruent. Isosceles triangle has two congruent sides, two congruent angles. So now again, because this doesn't have three congruent sides and three congruent angles, it's going to have less symmetry than the equilateral triangle. I hope that you can see that if you were to draw a line straight down the middle, That would fold this isosceles triangle in half, right? The left side, right side look identical, right? This is the only line of symmetry this thing has, though, right? There's no other way that I can draw a line that would fold it in half or make it flip onto itself. So because of that, this isosceles triangle only has one line of symmetry. So not all figures have a bajillion lines of symmetry, just might have a couple. Okay, so now let's talk about the second type of symmetry called rotational symmetry. All right, so let's talk about rotational symmetry. Rotational symmetry. So when we're looking for rotational symmetry, we're looking for a rotation, a turn, less than 360 degrees, less than 360 degrees. That maps a figure onto itself. We're looking for a rotation less than 360 degrees that maps a figure onto itself. So let us do the same two triangles we did before. So let's start with the equilateral triangle again. Again, try to draw all three sides the same. Right? So again, all three sides congruent, all three angles congruent. Now, typically, when we do these rotations, we think of the center of the figure as we're going to rotate about, right? So that's like a pin, right? We're just going to spin the triangle. So the question is, right, if I spin this triangle, can I, let's say we pick this point right here, can I make this point land on another point so that this figure, even though it turns, becomes itself again? And I believe I can. I'm going to go counterclockwise. If I spin it so that this point becomes here, I think the figure lands on itself, right? Then I think we could spin it again, and this point would land here. And then I think we could spin it one more time, and that point would land back on itself, and we'd be done. So what this means is, in 360 degrees, the triangle maps onto itself 3 times. 1, 2, 3. So in 360 degrees, a full circle, the triangle maps onto itself 3 times. To find the angles of those rotations, you are going to take 360 and divide it by 3. When you do 360 divided by 3, you get 120 degrees. So 120 degrees is the smallest angle of rotation. That's this first one. To get the next angle of rotation, you just add 120 onto itself. So if you add, 120, if you add 120, you're going to get 240. So here's the first one. Add 120. Here's the second one. If you add 120 again, you're going to get, and you get 360. And we don't count that, so we stop. So we would say that this triangle, this equilateral triangle, has 120 degree and 240 degree rotational symmetry. It is understood that every figure, if you spin it in a complete circle, will land back onto itself. So that's why we don't count the 360. Now let's take a look at the same isosceles triangle as above. So again, short, fat. 2 congruent sides, 2 congruent angles. So the question is, can we rotate this guy, right, around its center and land on itself? Well, let's think about this. So this point right here, right, maybe you think that we can go to here, right? Maybe you're like, oh, that point's the same. But here's what's going to happen, right? This tip right here is going to point down then. That's what's going to happen when you rotate it and stop there. So it doesn't map onto itself. That's bad, right? So it does not have that rotation. So unfortunately, I'll do it in purple, for the isosceles triangle, you have to go all the way around before it maps onto itself. What this means is it's going to have no rotational symmetry, right? It takes 360 degrees for the triangle to map onto itself. Therefore, it's going to have no rotational symmetry. So I just want to do a problem of each type from Delta Math, just kind of give you an idea of how they want you to show these lines of symmetry and the rotational symmetry. Okay? All right, so let me get out of here, and let's go to Delta Math. Okay, I'm going to try to do some random ones. So here, let's take a look at this one, okay? So it says, draw in all the lines of symmetry in the shape below. If there are no lines of symmetry, submit your answer without drawing them in. So notice when I hover over it, the dot comes. Now, if I'm looking at this, to me, this almost looks like an equilateral triangle. You see how nice it is? So I'm thinking that this thing's going to have 3 lines of symmetry. Now, they don't need you to be perfect. It's just as good as you can. So I'm going to start up here. I'm going to put a dot. I'm going to drag. I don't have to drag. I let go to here. So I think that that's going to split this figure in half. I also think if I go here to this bottom left corner and go towards the middle of this arc, I think that's going to split in half. And if I go here and go to the middle of that arc, that's going to split in half. So I think that those are the 3 lines of symmetry for this figure. I'm going to submit that. All right. Okay. Now let me go do the rotational symmetry. Let's see what we get first here. Let's get one that maybe has one. This one actually doesn't have any. Okay, all right, let's do this one, okay? So this is kind of a crazy figure, right? But if you look here, and I'll use my pen. So if I want to, so this is my center. Say this point, if I want to rotate it, let's see what happens, right? I can rotate this figure, and I believe it's going to land here, and here, and here, and here, and here, and there, and there, and there, and there, and there, and there, and back to itself. Oh my goodness, that was 1. Change colors. That was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I miscount. Hold on. Oh, down here. Oh, down. 1, 2, 3, 4, 5, 6. This is the 7th one. Sorry, 7. 8, 9, 10, 11, 12, 13? Is that right? 1, I'm sorry. 1, 2, 3, 4, 5, 6. Let me erase these reds. So, if I just count from here to the so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's what I thought. So 12. So this is going to have rotational symmetry. So does it have rotation? Yes, it does. So now once the smallest possible rotation that is possible. So what you're going to do here is, because it took 12 times to get back to itself, we'll do 360 divided by 12. Now I do 360 divided by 12, I get 30. So that means the smallest angle possible is 30 degrees. And every increment of 30 degrees to 360 is going to be a rotational symmetry. Now, it's going to have you try it. So watch what's going to happen. Let me clear my writing just so I don't mess it up. So look what happens when you press try. It actually spins. And you can see visually it lands back on itself. So you should have faith. Now let's just do one that we don't think works. So 40 degrees. Let's see. See how it goes too far? It doesn't land on itself, so you can tell that. But 30 degrees, let's just double check again. It does. So I'm pretty confident that is the correct answer. Okay, cool. All right, and you can see, right? It shows you all the different ones. 30, 60, see? All the way to 360. All right? Cool. All right, best of luck with this assignment, and we'll see you in class.